I can promise that you will learn one fundamental concept in chemistry after watching this video till the end. So today we will discuss about the SN2 reaction. So SN2 reaction is substitution, nucleophilic, and 2 is for bimolecular. So this is one type of substitution reaction. There are 4 types of reaction in chemistry. Those are substitution, elimination, rearrangement, and there is another type that is called okay, I will tell you. Just take forward that. Then I will come to this particular type of reaction. I pick up this slide from the slides here total. So substitution, SN2 is nucleophilic substitution. What is nucleophilic? Nucleophile. Nucleophile is attracted towards nucleus. Nucleus is positive charge, so nucleophile itself is negatively charged. So that will attract towards the positive charge. So in nucleophilic substitution, one of the nucleophile will attack to a substrate and one leaving group will depart from that substrate. You can see here that this is an haloalkane, X is an halide, so Y will come and Y is replacing X. Now this is called that is the nucleophilic substitution. Y is negatively charged, so it is a nucleophile. And parallelly, another reaction can take place. That is, Y minus can take one hydrogen from the beta hydrogen from the alpha hydrogen and beta hydrogen, and as a consequence, an halide can be formed. So this is an elimination reaction, and it is the competitive reaction along with the nucleophilic substitution. Now we'll come to the next slide. The nucleophilic substitutions are of 2 types. This SN1 and SN2. SN1 is substitution nucleophilic unimolecular and SN2 is substitution nucleophilic bimolecular. This 1 and 2 comes from the practical experiments. So this is the first order reaction and this is the second order reaction. So in SN1, what happens? The rate is fully depend only on the concentration of that substrate, that is the haloalkane. On the other hand, in SN2 reaction, the rate will depend both on the concentration of substrate and the concentration of nucleophile. So this comes from the practical experiment of a rate from this 2 type of reaction. We'll come to the next slide. So there are many things here to discuss. There is the reaction mechanism, kinetics, stereochemistry of SN2 reaction, factors affecting SN2 reaction, the structure of substrate, effect of nucleophiles, effect of leaving group, effect of solvent, phase transfer catalyst, role of ground. Then now SN2 reaction mechanism. So as the haloalkane, it is the carbon is sp3 hybridized, so tetrahedral geometry. So the halogen will depart and the halide will depart and the OH minus, that is the nucleophile, will attack from the opposite direction, and a transition state, after a transition state, it will form the product. So the transition state, you can see it is trigonal bipyramidal. Now, in transition state, the negative charge of OH minus, it is distributed both in Br minus, that is delta minus and delta minus, in both Br minus and on OH minus. And in the product, the negative charge came to Br minus. Next, the mechanism of SN2 reaction. So, you can see that if in a reaction, in a two transition state, you can see if the hydrogens are replaced with methyl, then that will create some steady crowding in the transition state. So as a consequence, the activation energy required for that type of substrate where there is more number of methyl group attached to carbon, that is the 2-degree carbon or 2-degree substrate or 3-degree substrate. So in that case, the activation energy requirement will be high. So those type of reaction will not go through SN2 mechanism. That will go from as SN1 mechanism. So the steric effect will affect the reaction mechanism, and as in SN2 reaction, inversion of configuration happen. If an optically active substrate is taken, optical activity shows where if a carbon have 4 different group, that is called optically active substrate. If this type of substrate undergoes SN2 reaction, then configuration change, inversion of configuration happens. That is, it will convert from R to S. Synthetic utility of SN2 reaction. A variety of functional group can be prepared employing a good nucleophile and an electrophile with a good leaving group. So you can see various type of reaction you can create by choosing different substrate and the nucleophile. So here the hydroxide will replace the chloride with the alkoxy group will replace the iodide. Then we'll come to the kinetics. In the reaction kinetics, the rate will depend, as I told earlier, both on the concentration of the nucleophile and on the substrate. So the rate equal to K into alkyl halide into nucleophile. K is the rate constant. So one power is from alkyl halide, another power is from nucleophile. That is a bimolecular reaction. From this, it comes as SN2 reaction. Next, the stereochemistry. As the if this is the orbital diagram of the substrate. The red is sp3 hybridized, and this is the antelope. The OH minus nucleophile will attack its electron density at the antibonding orbital of the CBr bond, and this bond will gradually develop, and this CBr bond will gradually break. And after that, inversion of configuration will take place. Here it is much more clear. That is the sp3 orbital CBr bond, OH minus one of the lone pair will attack at the antibonding orbital. Both the 5 coordinated transition state will form, and then it will convert again to sp3 hybridized orbital with the living group. Where inversion configuration happens. It is shown, same thing shown here. Again, the configuration changes from R to S, the same thing shown here. Now, SN2 reaction, the substrate structure should be less bulky, so that it should stabilize the transition state. Like if you compare the rate of this whole substrate, as the number of methyl group increases from up to from towards the down, the rate decreased. You can see the CH3 here, the rate is constant is 150, whereas in the tertiary halide, it is unreactive towards the SN2 reaction. Here it is it is described more easily. Like you can see that in the compound D, there is very little space. The carbon in the sp3 carbon is not exposed to the nucleophile, so it cannot attack from the backside. So that is why it is very much unreactive towards SN2 reaction. Again, the relative rate of these four halides, the CH3Cl, that is from the downwards, the rate has increased. The rate has increased. What is the reason? It is because there is an overlap happen with the p orbital of this CO bond, that is the sp2 orbital, and along with the transition state, those are both parallel, so overlapping happens. That's why the transition state gets stabilized. Here you can first CH3Cl, then one methyl group be increased. Then the transition state will be more crowded, so rate will decrease. And if you substitute with one OCH3 group in this CH3Cl, then the rate increased very much because the transition state gets stabilized with the electron density of the p orbital. So some overlapping happens, as well as in fourth substrate, again the sp2 orbital, that is the pi star orbital, will overlap with the transition state, and that will stabilize the transition state. So that's why the rate increases very much. Here you can see that pi star orbital of CO that will parallel towards the sigma star orbital of the CCl bond. So it gets stabilized. It is in transition state. CO or group stabilizes the transition state by the overlap of its pi star orbital with full p orbital of the carbon atom under atom. That's why the reaction rate is very high for such a substrate. SN2 reaction effect of nucleophile, as we described earlier, that the rate is depend on the concentration of the nucleophile and as well as the type of the nucleophile. So if you increase the concentration, the rate will increase, and with different type of nucleophile, the rate will increase. Like the nucleophilicity trend, with increasing the nucleophilicity trend, the rate will increase. down the group in the periodic table as the size increases, so that polarizability increases. So polarizability increases and nucleophilicity also increases. So the nucleophilicity trend is that iodide, bromide. Iodide is more than bromide, then chloride, then fluoride. And the second case, the conjugate base is more nucleophile than its corresponding acid. The conjugate base is more nucleophile because the electron density is very high of OH minus than H2. So it will easily attack to the substrate for a SN2 reaction. Polarizability, if you see that I minus, it is much more polarizable because it has higher size. That's why the rate with iodide minus will be higher than fluoride in SN2 reaction. Then again, effect of the nucleophile. It is alkoxy-OCH3 group. The reaction will take place in rapid reaction with methyl alcohol. It is very slow because the nucleophilicity of alkoxy is higher than methyl alcohol. Similarly, this is the conjugate base will be stronger nucleophile than its corresponding acid. This is the nucleophilic strength of some nucleophile. These are the strong nucleophile. Strong nucleophiles, it is phosphorus, sulfur, the size are larger, so nucleophilicity is higher, iodide nucleophilicity is higher, as well as the large electron cloud in this OH minus, CH3O minus. That's why these are strong nucleophile. And on the other hand, F minus, H2O, CH3O is the other weak nucleophile. Now there is the effect of a leaving group. A good leaving group needs to be a stable anion that are weak bases which can delocalize charges. So what is telling here that when the leaving group departs from the substrate, it must be stabilized. That is the negatively charged leaving group. The negative charge should be stabilized in the substrate. Now if you see that the F minus, the rate is 1. For Cl minus as a leaving group, the rate is 200. Br minus, it is 10,000. I minus, it is 30,000. And OTS minus, it is 60,000. Because here the towards the right, the negative charge will get stabilized from left to right. Now these sulfonate leaving groups, these are quite stable leaving, stable leaving, large as well as stable, because the negative charge it is very much stabilized with this 3 and this 2 double bonded oxygen. It will be distributed in this double bonded oxygen. If RO bond is RO bond is broken, then the O minus will form, and this O minus negative charge will distribute in all the 3 all sulfur oxygen bond, so it get stabilized through resonance. That's why it is the good leaving group. Effect of solvent. There is also effect of solvent in SN2 reaction. Solvent are of 2 types. One is non-polar and another is polar. For polar solvent, it may be a polar protic or polar aprotic. So solvent effect, SN2 reaction then it takes place more effectively in polar protic solvent. Sorry, in polar aprotic solvent, because in polar protic solvent, hydrogen bonding will take place with the nucleophile, and that's why nucleophiles are less free to attack. That's why polar aprotic solvent will be favorable, will be favorable condition for the SN2 reaction. Yes, there is the acetonitrile, dimethyl formamide, and acetone. These are the good solvent for nucleophile, because here hydrogen bonding cannot take place, but the reaction medium will be polar, because the polarity will stabilize the transition state and it will reduce the activation energy, and that's why the polar aprotic solvent will be the favorable condition of SN2 reaction. You can see this is an example. As the epsilon value increases, then the rate also increases. Now we are coming to the comparison. It is SN2 or SN1. If the substrate is primary or methyl, then SN2. If it is tertiary, then SN1. Strong nucleophile, so SN2. Weak nucleophile, SN1. Polar aprotic solvent, SN2. And polar protic solvent, SN1. Rate equal to rate constant into halide into nucleophile. Rate equal to rate constant to halide, concentration of halide. Sorry, concentration of halide, yes. And it in inversion of configuration takes place. Here racemization will take place. No rearrangement takes place. Here rearrangement product will form. Now important substrates. These are the important substrate for SN2 reaction and as well as SN1 reaction. Here, if the living group departs, then a carbocation will form and it will be stabilized through resonance effect, plus R effect. This is also a good compound for SN2 reaction also, because the transition state here gets stabilized with the pi star orbital of this double bond. So both the substrate are good for both the reaction SN1 and SN2. Here it is described. Now vinyl and aryl substrate, these are very much reluctant towards SN2 or SN1 reaction, because the carbocation which will form after depart of the living group, it is very much unstable, because an sp2 hybridized carbon will carry the positive charge. As you can see that, sorry, sp carbon, the aryl cation, that is highly unstable. And as well as if you can see that the antibonding orbital is not easily accessible for the nucleophile, because the benzene ring is here. So SN2 reaction will, SN2 as well as SN1 reaction will not take place from vinyl or aryl substrate. You can see here that nucleophile will not attack from the backside of the benzene ring. The attack is not possible. For cyclic system, here you can see that bridged carbon, if that is a in bridged halide, it will not take place, because the carbocation which will be formed, which cannot be formed. Carbocation is planar geometry, so planar geometry will not maintained for this at the bridged position. So due to static rigidity, SN2 reaction will not happen. And also you can see that nucleophile cannot attack from the backside of the beer, because it is a cage-like structure. The antibonding orbital is not accessible to the towards the nucleophile. So there is a problem. Now SN2 reaction by O18 E2H. You can see this is 1 degree halide. This is 1 degree halide. This is 2 degree, 3 degree. So the rate will increase from left to right as the transition state will be crowded, activation energy requirement will be higher, so rate will decrease. The rate of soluble issues is this is 1, this is 10 to the power minus 6, 10 to the minus 14. Here the reaction cannot take place as it is rigid structure and it cannot maintain the planar geometry, but here the rate is 10 to the power minus 6, quite higher than this substrate because the number of carbon atom in this chain has increased. So that's why it can maintain somewhat planarity in the transition state, and that's why the rate is quite increased. And in the first halide there is no problem. It is the 3 degree carbocation can be easily formed. It will be stabilized both plus I effect of the 3 methyl group as well as hyperconjugation structure of this 9 hydrogen. So the rate will be high for this substrate. I will come to the B. In B, for the substrate 1, the planarity will be maintained and all the benzene ring will provide Placer effect and will stabilize the carbocation through Placer effect. Whereas in this compound the planarity cannot be maintained because it is a cage-like structure, rigid structure, so planarity cannot be maintained, and the p orbital of this carbocation is not parallel to the pi orbital of this benzene ring. It is actually orthogonal. That is perpendicular to each other. So this is the complete SN1 reaction. Guys, if you like this video, please share with your friends and also subscribe the channel to get more such videos. Thank you. Have a good day.